Let us talk about a classical problem in game theory known as the prisoner's dilemma. See, Tom and Jerry are arrested for a crime. They're placed in separate cells and they're told the following. They called out one by one and they're told the following. They have two choices to make. Either they can snitch on the other, that is betray, or they can choose to stay silent, that is cooperate. And they're asked to make one of the choices. So the consequences are as follows. If both Tom and Jerry end up staying silent, if they end up cooperating, they get 4 years in prison in total. That is 2 years each. If Tom ends up cooperating, that is, if Tom ends up staying silent and Jerry betrays, so Jerry gets to go free, scot free, while Tom gets 10 years in prison. The same goes for Jerry as well. If Jerry ends up staying silent and Tom betrays, so Tom gets to go free and Jerry gets 10 years in prison. And the last choice is the scenario in which like both of them end up snitching on the other. So in that case, they get 5 years in prison each. So given that they have no idea what the other person is going to decide on, what would be their optimal strategy so as to get the best possible payoff? So clearly, from the group perspective, it appears that they both end up cooperating, that is, staying silent and get out of the prison by spending 2 years in prison each. But since they're in separate cells and they have no idea what the other person is going to do, the logical thing would be to analyze what would be the best strategy given that the other person can make any possible choice. So I was Tom, if I was Tom, I need to pick a choice irrespective of what Jerry decides. So if Jerry ends up staying silent, if Jerry chooses to cooperate, then the best choice I can make is to betray Jerry. Because that would mean I get to go free right now while Jerry gets 10 years in prison. If Jerry ends up betraying, then the best choice I can make is to betray as well. Because otherwise, that would be bad news for me. I would have to stay in prison for 10 years. As you can see, irrespective of what Jerry decides, that is, irrespective of whether Jerry cooperates or betrays, the best choice for me is to betray. Similarly, the same argument goes the other way around as well. For Jerry, irrespective of what Tom decides, the optimal strategy for Jerry would be to betray as well. Because if Tom cooperates, then Jerry can get to go free by betraying. And if Tom decides to betray, then Jerry has to betray as well. Otherwise, Jerry would appear like a fool. So, irrespective of what the other party makes, the best choice for both of them is to betray on each other. And this stable state, is called the Nash equilibrium. And the rationale is that even though this state appears to be giving us a better payoff, that is just 2 years in prison each, and it is the right thing to do. However, this state happens to be unstable because both of them have an incentive to change their strategies. Like for example, um, if both of them are choosing to cooperate, then a person has an incentive to change a strategy to betray, and he gets to go free. Thus, it is not stable. So at the end of the day, Tom betrays on Jerry, Jerry betrays on Tom. They both end up snitching on one another, and they end up spending 5 years in prison each. because of what is known as Nash equilibrium. So, if you watch The Dark Knight and you do remember the scene about the Joker's social experiment.
Tonight you're all gonna be a part of a social experiment. I'm ready right now to blow you all sky high. Anyone attempts to get off their boat, you all die. Each of you has a remote. Blow up the other boat. At midnight, I blow you all up. If, however, one of you presses the button, I'll let that boat live. So, who's it gonna be?
You'd see that that scenario, that experiment, was indeed a variation of the prisoner's dilemma, and where boat A has a choice to detonate boat B, and boat B has a choice to detonate boat A. And the Joker's confidence came from the fact that this state, where both the boats end up detonating each other, happens to be the stable state or the Nash equilibrium. And even from a rational perspective, boat A is better off detonating boat B, and the same goes for boat B as well. And thus, they both will end up pressing the button. But clearly, from a moral standpoint, that is a terrible choice to make. And that happens to be the case in the movie as well, where both the boats ended up cooperating, and they ended up picking this choice, even though the Joker did add, state that he, in the event that they both end up cooperating, he would blow off both the ships anyways by midnight. So that was an interesting take on Prisoner's Dilemma. So we saw that Nash equilibrium provided stability. No player had anything to gain by changing only their own strategy. And this was a very famous result shown by John Nash, which eventually got him the Nobel Prize. It was that every finite non cooperative game has at least one Nash equilibrium. So, this is about the existence of Nash equilibrium. And however, the problem of finding Nash equilibrium was shown to be computationally intractable. Uh, the specific results were that the problem of finding Nash equilibrium in 2-player games, 3-player games, and 4-player games was shown to be PPAD complete. We'll talk about that in the upcoming videos, but the real problem with this equilibrium is that this equilibrium for a set of players, all acting rationally in their own interest, may not be the outcome that is actually best for those players. So, stability doesn't really guarantee the best possible outcome for the players. So, what do we do in that case? Maybe we shouldn't just try to change the strategies. Maybe we should change the game itself. And that is the intuition behind mechanism design, what is sometimes also known as reverse game theory, wherein you try to design rules that will give you the behavior you want to see, rather than trying to come up with strategies in the game that is given to you. So let's try to revisit the same prisoner's dilemma, which did not give us the optimal outcome that we would like, and let's see how we can change it. So one possible way is to introduce an external agent. So let's say Tom and Jerry were part of a crime organization, and the crime mafia boss has stated clearly that the informant would be killed. That is, the person who would end up snitching would be dead. So, in that case, let's see how the game changes. So, clearly, what was the Nash equilibrium in the previous game will not be the equilibrium, as the person who ends up snitching would be dead. So, in that case, Tom has just one choice to make, that is to stay silent. And similarly, Jerry has just one choice to make, that is to stay silent. They both end up cooperating, and that turns out to be the new equilibrium. And as you can see, by changing the rules of the game, in this case, we brought in an external agent, and by modifying the payoffs accordingly, we have got the outcome that we require. So that is it for this video. Do subscribe for more interesting takes on game theory. Thank you.